Hi, another video on the ring light project and some really great feedback since the last video, so I really appreciate some of those comments and I've used those to make some modifications on the PCB. So let's get straight into it and have a look at what's going on. So here is the new layout and you can see it's quite different to how it was before. Now one of the comments which I really liked is about the positioning of the brightness and the power switch, and it makes a lot more sense to have it on the side, which is where you're naturally going to reach with your hand. Considering the focus adjustment is on the side as well, it makes sense to have the brightness control and the power switch on the side. So I pretty much just lifted the layout exactly as it was, rotated it 90 degrees and moved it up here. Now the other thing that meant is that then the DC to DC converter that was previously sat here had to move, and what I've done is I've ended up moving them to the side here. So this top DC to DC converter controls these two LEDs and the bottom one controls the bottom two. And in terms of the loop area, it's actually no different really. We had, for example, the DC to DC sitting between the two boards. We're just adding a very small amount of length on the current carrying conductors here, so we shouldn't see too much of a problem. And that's also meant that we've got the two DC to DCs lined up with all of the components in the same place. I've increased the thickness of the areas around some of the pins here, so you can see these ones that are carrying the higher currents. I've used much wider tracers and some polygons here to do those shapes so that we get the best performance. Now there was one really useful comment which prompted me to have a little think about what I was actually doing, because I was kind of following the datasheet quite blindly and it had an example layout, but the comment obviously highlighted that inductors are magnetic devices and there is a possibility of inducing eddy current. So when you've got a current flowing in the inductor, you get magnetic lines of force all the way around, and when these pass through a conductive trace or the ground plane, for example, then you're getting eddy currents induced into that conductor. And what can happen is, because these are there to counteract the magnetic lines of force, the inductance is reduced and also the Q factor of that inductor falls, so you increase your losses in the design. So what I've done is I've cleared out some area here so there's no conductors or anything passing underneath that inductor, and that should mean that we get better performance from this DC to DC converter. And it should also improve the EMI performance, because even if you don't have a conductor that passes all the way through to create one complete loop through the magnetic lines of force, what can happen is if you've got excessive traces under here or polygons bigger than they need to be, they can be an antenna for the EMI. So by reducing those as far as possible, unfortunately I couldn't quite get rid of this little section here, but it's certainly better than it was. So we've got this clear area underneath the inductor, and that should mean that we get much better performance. Other than that, there's not a lot that has changed. I've just got the power LED at the front here, and what we'll probably do is in our 3D printed case that we're going to make, there'll be either a cutout or something made from some clear plastic to act a bit like a light pipe or something so we can see the power LED. Now we can just quickly do the 3D view. It's not particularly good in this version of Proteus, but I've sorted out the center section, so that should get cut out properly, and that's basically what this PCB is going to look like. And then I'm expecting that there's going to be some kind of 3D printed housing that goes around it. And what we're going to do today is just quickly try and design these LED boards that are going to sit in this section here. Right, so just a reminder for everyone what's on the LED boards. There's 4 of these LED boards per ring light, so 1 in each corner, and all it's got on it is the XHP 50 LED, which is basically 4 LEDs in one package. We've got 1 capacitor on there, and then 1 connector, which is basically just 3 sill pads, just so that we can wire across from the main power supply board. Now what I've done is I sort of copied across the layout into the PCB tool and then cut everything out, and it's left us with the PCB size that I had planned for on the original ring light, because I drew these in, and also the positioning of the connector on the power supply PCB so that we can place the other one correspondingly in the correct place. So the first thing that we need to do is basically work out how this is going to sit. Now the plan is that it's probably just going to have some flexible wires to the main PCB, and then I think there's going to be sort of 4 screw holes in this board to hold the PCB into the 3D printed case. And whether we manage to get some movement so that we can adjust the angle in the case, that depends on how much time I have to do the mechanical design. But basically, I think the lens is going to sit in the middle with the LED bang in the middle of that. The tracer's coming out to a connector, and then some mounting holes around the outside. So we can now start placing the components. Let's start off with the lens, which needs to be somewhere central, horizontally speaking. I think it's going to be pushed slightly towards the top of the board here, but we do need enough space in each corner for the mounting screws. So for now, we're just going to place it approximately here. We'll have to check it's bang in the middle in a moment. And then we want to place the connector. Now, the main power supply board is going to have the components on the top side of the board, and these LEDs are actually going to be on the bottom side. So when we place this connector here at the bottom, we do need to rotate it. So we'll place it somewhere around here, and then we'll spin it around 180 degrees. And when it's the other way around, then all of these numbers will line up. Then we're going to have our capacitor just across those pins, and that can go somewhere just there. We'll move the reference designator out of the way slightly so we can actually see what's going on. And then we just need to place our LED, and that wants to go in the center, and this should line up perfectly with that just there. And so the next thing we need to do is just put some mounting holes in, and we're almost done with this PCB other than the tracking. And then we've got to have a think about the heat sinking and how we get all of the heat out from the LED, because potentially this is dissipating quite a bit of power. Right, so I've just measured the heat sink. It's one of these little devices. It's 25mm by 28mm, and this doesn't need any mounting holes because we're going to be using one of these thermal adhesive pads to stick it onto the board. So here is the outline of that, and basically it wants to sit here centrally on that LED. And then we want to have our mounting screws. Now it may mean that we need to move this LED down a little bit. They want to be M3 pads, and so we're probably going to hit that heatsink with it where it is there. At this end we've got plenty of room, so I think we're going to need to nudge the LED down a little bit. So I've drawn a box inside the overall PCB outline that's 4mm in from each edge, which means that we should have enough for the screw head. And so we simply want to place some pads exactly on these corner parts here. So that's one in the corner here. So that's that done, and now we need to have a think about the thermal considerations for this LED. So if you take a look on the website for the power LED manufacturer that you're using, they normally have some really useful application notes, and the Cree one has these ones about thermal management for the LEDs. And if we take a look through this one, it shows how to build up a picture for the thermal performance. Now you can put all of this into a piece of simulation software like ANSYS or something like that and model it, or you can do it mathematically and make some estimations. Now, because we're not driving this at particularly high powers, it is quite high power, but we're not using this anywhere near the maximum power ratings for these LEDs, I'm quite happy just taking a fairly basic approach to looking at the thermal performance. Basically, we want to get as much heat to this heatsink as possible, and then if we need to add some forced cooling to this, then that is what we're going to do. I'm not going to go through and do the detailed calculations. So, but it does tell you how to implement the design. So first of all, they're talking about putting thermal vias under the thermal pad, because on these LEDs, there is a thermal pad in the middle, and that's basically where the die sits, and that's where all of the heat comes out from the LED package. Very little heat comes out the anode and cathode connections to the LED, so most of it's coming out of here. And by having some thermal vias, which are standard vias, they're just called thermal vias because they're there to get rid of the heat, that can draw all of the heat out from underneath the LED and bring it onto the bottom layer of copper on the PCB. So you can see here we've got them going through, and then the heat goes through the copper and down onto the bottom layer. Now the problem with this is that when you come to apply the solder paste to put the LEDs on your PCB, what can happen is the paste can end up just disappearing down these thermal vias, and then you don't actually get very good performance of the solder paste onto the LED. So they've got some suggestions here on how to improve that, and they've got a bit of discussion here about whether you have open or filled vias. Now with many PCB manufacturers, you can specify whether you want the vias to be filled with either copper or some other plugging material, or whether you want them open. Now open vias gives you the best thermal performance, but that's where you tend to see all of the solder just disappearing down the vias. Now they're suggesting here that if you manage to keep the diameter of those holes less than 0.3 millimeters, the surface tension of the solder will actually stop it wicking down and ending up on the bottom layer. So JLC PCB do have the ability to drill holes all the way down to 0.2 millimeters for your vias, so we can definitely achieve that, and I think that's what we're basically going to go with. Now they have also got some recommended footprints, sort of this H shape. They're showing it on a star-shaped PCB, but I think they had some other examples in the datasheet elsewhere. Basically, you want to spread that heat out as far as possible on both the top and the bottom surface. So you can see here, they've got the two conductors for the anode and cathode, and then this is where all the heat's going. You want to spread the heat out on the top layer with the thermal vias directly under the LED, and then on the underside just have one big pad, and that's what we're going to do. That pad is going to be the same size as the heatsink, and then when we've got the thermal pad on here, that's going to try and transmit as much heat to the heatsink and then dissipate it into the ambient air. Now what we've got here is a whole grid of 0.25 millimeter holes, and these have all been assigned to the heatsink net. So if we look here, net heatsink, that means it's automatically got connectivity to this pad here. What we're going to do first of all is just route the tracers for the cathode and anode, and rather than go with this shape that they're recommending, I think I'm just going to flood the PCB with a copper pore that is also connected to this heatsink net. So let's connect up the tracers. We only want the tracers to be on the top side for these two nets, because what we actually want to do is on the other side we want to have it all copper connected to the heatsink. So we can bring this down. So next we want to fill both of the layers with copper, all connected to this heatsink net, and to do that we can use the power plane generator, connect it to heatsink, press OK, and you can see it's filled the bottom copper with copper. But if we highlight it, you can see it's not created a solid piece of copper around here, because the default setting is to relieve pins. And what that means is there's what's called thermal reliefs, and that means that it makes it easier for you to solder components to any pads. We don't actually want that. We want this to be solid copper. So we go to the properties and we uncheck the relieve pins, and that should give us solid copper on that side. And we just repeat that again for the top copper. And there we've got our solid copper top and bottom. And then automatically all of these vias are connected up to the heatsink pad. So that's actually all we need to do on this PCB. I'll just tidy it up, and then we need to start panelizing the board so that we can make lots of these in one go. So here's our finished PCB. This is just one single board with one LED on it. Now it doesn't make financial sense to just make a single board. What we want to do is panelize it, considering it's quite small. It's 35mm by 40mm. So we should panelize these, which means having multiple boards on one panel. And if we go to JLC PCB, you can see that I've selected panel by customer in a 2x2 array. We want the PCB thickness to be 0.8mm so that the heat is transferred more easily between the two layers through those thermal vias. We want a white PCB so that we don't add any colour to the light that's being transmitted from that LED and through that reflector. And then also I want the immersion gold finish, just so that the PCB lasts a bit longer in storage. Now I'm going to assemble at least 4 of these LED boards to make one ring light, but I may end up using these LED boards for something further down the line, so I do want them to be solderable in a couple of years' time, for example. So if we have a panel 2x2, it's going to come in somewhere around 100 by 100mm, and you can see the cost here is about $57. If we increase the size to 150 by 150, we can at least fit 3x3 there, and that's only increased the price by $5. So it definitely makes sense to do that. And that's where you want to have a play around with some of these figures and work out what makes sense. Because if we make it a little bit bigger, in fact, I don't think these numbers in the panel format make any difference. It's not hugely more expensive to make a panel that's quite expensive once you're picking some of these specialist options to start with. Now in the PCB tool that I use, which is Proteus, at least in this version, which is version 7, there are some newer ones out, the Panelization tool isn't particularly user-friendly. Basically you enter the Gerber viewer, and then you have to copy and paste your design multiple times in here, and then manually do all of your cuts and all of the mouse bites and everything else by hand. It doesn't do any of this automatically. Now you might ask, why can't you just duplicate the layout in the PCB layout tool? And the reason is that the reference designators would throw DRC errors, because either you would end up with the reference designators incrementing for each PCB, and that wouldn't exist in the schematic, or you would have multiple PCBs with exactly the same reference designators, and therefore it would throw up a warning because it thinks you placed multiple parts of the same item. So what you have to do is lay them out with the correct spacing, and then you have to create a new board layout. So we're going to draw a board outline over all of these PCBs, and then we have to draw where the routing is going to occur within the panel. Right, so what I've ended up with is a panel of 9 PCBs, and you can see what I've done is this grey layer here is the mechanical 1 layer, which is the router layer that JLC PCB use to cut the slots into PCBs. This is set to 1mm thickness, which is the diameter of the cutter that you use at JLC PCB. They don't have any finer cutters. If you choose a wider thickness, I think they just use the same 1mm cutter and do multiple passes to increase the thickness. So 1mm. And then we've got this little section, there's 4 of them, 1 on each side, and the gap between the 2 points here is about 0.8mm. So there's simply 0.8mm of FR4 material here, just keeping the PCB within the panel. So all of this section around here is FR4 material that will be wasted. Then we've got all of the cuts in grey, and then our actual usable PCB is the section in the middle. So we'll just output the Gerber files, and we've got all of the correct options selected, so we should be able to save that. And then we can try uploading this to the JLC PCB website. And there we go, that's uploaded successfully. You can see we've got our 9 PCBs within the panel, and the overall size has come out 150 by 135mm. Now we only need 5 boards because that's going to give us a total of 45 LED boards, so we've got way more than we need, but 5 is the minimum order quantity. We've got 1 different design of PCB. They do charge you more if there's different styles in there. Panelised by customer in a 3x3 arrangement. You can get JLC PCB to panelise the board for you, but it's simply V-scored, so you can't have any curves or anything like that in the routed out sections. We want a white PCB with immersion gold finish, and we want it 0.8mm thick. And I think that's all of the settings we need. White, gold. May as well remove the order number. And there's our preview. So they've included the new colour in the preview here. And that's coming out at $63.63. And then it's estimating shipping at around $24 with DHL Express. That means it normally gets here actually within 3 days from the point where it's shipped. And the DDP here means that the tax is already paid. So although the tax is, your normal 20% or whatever the VAT is in your area, when you get it shipped by DHL, they normally add a fee to it of something like £12, which is usually ridiculous in proportion to the amount that you've ordered. So by doing the DDP delivery method, it does mean that you save a little bit of money. If you don't want to do that, then it's $21. So you're only paying $3 extra for the tax and everything paid for. So we can save that to the cart. And then what we'll do in the next video is order the main PCB and do the pick and place and all of that stuff on it. So hopefully you found the video interesting. Any comments, don't forget to leave them down below. But until next time, thanks for watching.